Okay, our second talk will be given by Professor Auroop Ganguly. Professor Ganguly is a civil engineer and hydrologist, a computational climate scientist, and a researcher in machine learning, extreme value theory, and nonlinear dynamics. After earning his PhD from MIT, he has 24 years of professional experience at Oracle Corporation, Oak Ridge National Laboratory, and since 2011, Northeastern University. His work has been published by Nature, PNAS, and Nature Climate Change, and includes award-winning papers in ACM KDD and SIAM data mining, in addition to 2 US patents. He's been widely quoted in the national and global media, is a fellow of the American Society of Civil Engineers, a senior member of both ACM and IEEE, and recently co-founded a successful startup company in urban climate resilience, which has been acquired recently by a Fortune 500 company. The title of his talk is A Convergence of Complexities in Climate Systems and the Role of High-Performance Computing. Please join me in welcoming Professor Ganguly.
Thank you so much for kindly coming to this talk, which is a bit offbeat from the usual, I think, the supercomputing talks. But we do use a lot of supercomputing in this domain, as you all know. First of all, I'd like to thank my current and former SDS lab, Sustainability and Data Sciences lab members, students, postdocs, visiting faculty, and others. And also funding from NSF, DOD, DHS, DOE, including Oak Ridge and PNNL, and NASA. So let's start with a prologue. The ozone hole problem. We, as in the royal we, as in the very royal we, human beings, we have, I wouldn't say solved it, but we have gone significant ways there, from science to globally coordinated action. Unfortunately, I would not say the same for climate change. Let's look at this, what the state is. So 1974 is when Mario Molina and Sherwood Rowland published their paper in Nature on stratospheric sink with chlorofluoromethanes, which can lead to ozone hole. 14 years from that science, we had action. The action was happening, but we had demonstrated action. The Montreal Protocol, it was finalized. And 7 years after that action, there was a Nobel Prize that was awarded. So science to action to a Nobel. And if you look below, this is where we are now. The Kigali Amendment to the Montreal Protocol was signed by 100 parties in 2020. Even the United States signed it last month. And as a side benefit of this amendment, which was designed to stop the ozone hole, as a side benefit, we'll get reduced global warming as well. So overall, lots to be done, but still a success story. The climate problem is interesting, though. 2007, there was the Nobel Peace Prize in climate. This preceded the economics Nobel, if we can call it that, which was 2018. Roughly, I would say that is climate adaptation, mitigation, the science of that, or one aspect of the science of that. That was 2018. So 11 years for adaptation to catch up with what should be the impact, which is the peace. And the physical science basis, which is what it's called in climate, that one was just last year, won by some scientists who do climate simulations and attributions, climate data science, as well as complexity scientists. So it's almost like the other way around. And if you look at the situation currently, here is one of the Nobel laureates saying that, I hope that young people succeed where we scientists have not. And New York Times last month says climate pledges are falling short and a chaotic future looks more like reality. So what is going on? If we know how to translate science to globally coordinated action, something is a bit different here. Well, first of all, if you think of the risks associated with climate and what needs to be done, it's a complex problem, arguably more complex than even the ozone hole problem. So we are talking about policy myopia. We are talking about financial disincentives that are often built into our systems, such as insurance flood programs. We're talking about scientific and engineering stagnation and outdated best practices. We're talking about uncertainties that cascade from socioeconomic what-if scenarios, which give us carbon trajectories of the future, to prediction with, or in climate we call it projection with Earth system models or global climate models, bringing it then down to stakeholder scales, which is downscaling, and the impacts and the economic damages from natural hazards to ecosystems, food, economics, welfare, internal and external migration. So the problem is fairly complex, as I was saying. And that could be one of the reasons, but I think there is still a need to understand some of this even further. Some of us, when I was at Oak Ridge Lab, we participated in climate war games organized by a Washington, DC-based think tank called Center for New American Security. This was way back in 2008. But one thing that these war games, and by war games I just mean simulations with humans, not with computers. So these war games, an actual conference of parties, and you may have been following the COP27 in the news, what they have told us again and again is that each nation, each party will act to reduce emissions and control emissions to the extent that it matters for them, whether it's in the context of resources such as food, energy, water, ecosystems, whether it's in the context of natural hazards and humanitarian aid, whether it's in the context of population growth and movement both within a nation and externally, and things like deforestation, afforestation. What it means for that nation will invariably dictate. So although adaptation, which is managing the unavoidable, or has been called that, and mitigation, which is adaptation is managing the unavoidable, mitigation is avoiding the unmanageable. They are interlinked, but it's clear that it's adaptation interest, self-interest of each party that dictates what happens with emissions policies. So that adds to that level of uncertainty. Some of us have been participating in various ways in the panels, in review panels. There is one United Nations panel which actually looks at the intersection of ozone hole, the stratospheric ozone depletion, and radiation and climate change, both combined effects and how one impacts the other. I think there's a lot of lessons that still needs to be learned, both for natural systems, but also for human engineered and social systems. With that prologue, now let me come to some certain things where high-performance computing might be relevant, or the kind of needs that we may have in climate. Let me preface that by saying I'm not an HPC person. I use some of it. The kind of things we have done in a very focused manner, and HPC, and here's my pitch. You can find it at the Massachusetts Green High Performance Computing booth for Northeastern University right here, done by one of my PhD students, Jack Watson. But here I'm going to talk a little bit into the kind of challenges that we see coming out. Simulations is at the heart of what we do when we talk about predictive understanding of climate. We are talking about long lead times, and of course we don't have observations in the future. Simulations is what we rely on, and these are simulations of partial differential equation-based systems together with their parameterizations. And these, of course, it's well known that these take a lot of the compute time and resources of the world's largest supercomputers, including the ones at Oak Ridge National Lab. But where are we going now? So first of all, still talking about simulations, I talked about Nobel Laureates, and this is in the 1970s. On the left, this is the 1995 chemistry Nobel Laureates who talked about the ozone hole problem with their laboratory experiments and the experimental facility. And on the right is one of the physics Nobel Laureates last year who got the climate physics Nobel, and with a computer. And I'm sure the experimental facilities have improved significantly since the 1970s, but I don't need to tell the audience here how much computing has improved from then. In fact, we could potentially argue that a division of curiosity-driven science versus mission-driven science is almost a function of the kind of computing we use. So if we think in climate, when we are looking at simulations, generating the science for simulations, understanding what those simulations mean, trying to improve them with AI, potentially understanding human dynamics there, we're still in the realm, if you will, of curiosity-driven research. You still need high-performance computing, such as this mass green computing high-performance center. But for the simulations, the large-scale Earth system model simulations, that's where we need the large supercomputers. So what do I mean by this complexity of convergence, and what kind of solutions, what kind of things are we looking for? So in the natural Earth system, we are talking about chaos. We are talking about not just the English definition of chaos, but mathematical chaos, which is extreme sensitivity to initial conditions, and things like strange attractors. Ed Lorenz showed this for the weather system. We have equivalents of that in climate system as well. So you're talking about complexity in that sense. And spatiotemporal machine learning, computer vision, these are the kind of things that have been used, we have used, others have used, to try and improve our predictive understanding. When we talk about human-engineered systems, which are impacted by climate hazards, climate change, whether it's water systems, power grids, and so on, transportation systems, what has been happening is the world, as we all know, has been growing more and more interconnected. And usually there is a good reason for that. We do that because we get benefits from each other. But what that also means is that if there is a failure, if some of these intensifying extremes happen to cause even a relatively small failure, that failure can percolate across an interconnected system and then cascade across what we could call system of systems. And there, we think of probabilistic graph, that aspect of machine learning and uncertainties and causal flows as trying to handle that. And the third aspect is social systems, human institutions. The complexity there, in addition to many other things, derives from the tragedy of the commons. We all own something, therefore none of us feel responsible for that thing. And think of infrastructures, think of environment, and also certain financial disincentive structures built in. Despite Professor Elinor Ostrom, who was the first woman economics Nobel laureate all the way in 2009, talking about various ways to manage these systems, we have not evolved yet to a stage where we can fully understand and manage these. And these, by the way, are, this is one area where agent-based modeling could help. So if you think of a broad, if we think of artificial intelligence broadly construed from machine learning to probabilistic graphs and network science and agent-based modeling, in the natural systems, human-engineered systems, and social systems and institutions, there are certain things we could do, and that's where that complexity or convergence of complexities come in. Now, in general, when we think about AI, though, first focusing on machine learning, it's also going in a very interesting direction. We talk about these foundation models from Google, Microsoft, enormous, huge models which you need to pre-train with data that may or may not be exactly related to your problem, but then you focus it on your problem, that pre-trained model, and it seems to work. These kind of things may quickly get beyond the realm of what could be done in academic labs. Just as currently academic labs and curiosity-driven research in general, even in government labs, just as from that perspective, we can build part of the science, we can test the science, we can examine the simulations, and so on. The science I'm defining broadly, natural sciences, engineering sciences, social sciences. But we cannot run these Earth system models, the integrated Earth system models in academic labs. They have to be run with significant resources, with the largest of supercomputers. Is machine learning going in that region? I don't know yet, but there's a strong possibility. And where we are with machine learning, well, we still don't fully understand this. These are two on the right and left. These are two papers from other groups in the proceedings of National Academy of Sciences. One talks about the unreasonable effectiveness of deep learning. And the other talks about reconciling deep learning with what could be called Occam's razor, bias variance trade-off, basic principles of science. It's at that interesting stage. And of course, then there is agent-based modeling, which have been used successfully in some areas, such as epidemiology, and has potential applications in human-driven systems in Earth and climate sciences. Let me quickly take you through a case study which illustrates this convergence of complexity and megalomaniac that I am. I'll just take you through two news articles and some corresponding work from our own lab, which illustrates that and which quoted me, just because I happen to read those articles and just because I happen to know a bit more. But there have been a lot of such quotes, a lot of such work from the entire community. I'll take you through one of them, or one set of them. So here is Newsweek talking about global weirding. Humans have caused chaos in Earth. And this chaos is not chaos theory. This chaos is just the English definition of chaos. And, so one thing that I was telling here are a couple of things. One is when we think about these kinds of what has been called global weirding, we need to think about the hydrometeorological hazards, whether it's hurricanes, rainfall extremes, floods, etc. But we also need to think about the exposure and vulnerability side of things, the human side of things, if you will. There is anthropogenic warming on the, emissions-related warming. So that's one part of the human-related thing. But here I'm talking about exposure, vulnerability. Even if the same hurricane, same intense hurricane were to hit today at many parts of the world, it would cause much more damage because of societal and infrastructural vulnerability. So both aspects need to be considered. And the other thing is we are seeing more and more, and I'm not sure if we have a clear understanding why yet, but the systemic variabilities and the inherent uncertainties seem to be slightly increasing, and we don't yet have a good handle on characterizing those. And these limits to predictability, we still have an idea of how to deal with that in weather systems. In climate systems, we don't. And this can cause complacency in our design. And this can lead to surprises which can be problematic for us. So we need to understand this better. Anyway, to talk about just intensifying extremes under climate change, here is just one of our work, and this is the entire community has been working on many aspects of that. This is just one work in Journal of Geophysical Research, which showed intensifying precipitation extremes under global warming, and the aggregate statistics of these precipitation extremes. For example, in this case, there is a clear signal there. Things like, the 30-year levels projected to become 10-year levels, 5-year levels, etc. And also, some of this could be translated to design curves, design for hydraulic infrastructures, water resources management. Here's the other article I wanted to mention. This is a New York Times article which talks about 3 ways to build back smarter after Hurricane Ian. And what I was trying to make a case there is that if we build back in the exact same spot, in the exact same way that we have done so far, we are subject to the exact same risks. We are not reducing the risks. So we have to do something a bit differently. And there were 3 things that were discussed here. One is building codes, or structural or infrastructural codes, if it comes to that. They have to be a little bit potentially less prescriptive and more performance-based. design based on performance. We need to rethink in some cases what kinds of reliability measures we need. Second is this combination of gray and green infrastructures. They have different kinds of impacts on ecosystems, different ways in which they can safeguard human lives and property, and different ways in which they can hedge against future uncertainty. So a combination of gray and green infrastructures and defense systems. And the last part is, despite doing all of those, in some cases we have to remain open to the possibility that certain parts of the world and this country are not livable anymore. The risks are too high. We cannot force people usually to leave a certain place, but there could be financial incentives and disincentive structures built in. However, we have to be a bit careful that that doesn't lead to forced gentrification, so it has to be equitable. So those are the three kinds of things. And some of the, just as one example, one of the work that has been done in our group is to look at multimodel ensemble, different model ensembles from climate, look at what has been called the irreducible uncertainty, the internal variability, as well as model spread, and try to see if we can transform that into what are called design curves. These are curves, intensity, duration, frequency, depth, duration, frequency, obtained from these large climate model simulations and observations, and then used for design of hydraulic infrastructures or operations. So if we can include some of these uncertainties and some of these intrinsic variability and uncertainty, they are interrelated, not the same thing. But if we can use them for these kind of design curves. So going from climate extremes on the one side to robust infrastructure on the other, I was just trying to show that through a couple of news articles and just one example of our own work. And again, I'm showing these new articles in our own work only because I know a bit more about them, but there's an entire community which has been working on this. So now I'll talk a little bit about some case studies and the gaps that exist, and try to motivate a bit about where HPC could come in and how it looks so far. These case studies are completely based on almost completely, I would say, based on our own work at our lab at Northeastern University, and some before that at Oak Ridge National Laboratory. But hopefully they'll be illustrative. So I'll talk about three broad areas: physics-based large-scale simulations. I'll not really talk about the simulations per se, which already exist and which are already being done at these 40 to 50 modeling groups across the world, including groups, 4 groups now in the US, NASA, NOAA, NCAR, and DOE now has its own Earth system model. I'll talk more about what can be done with that, what kind of insights we could get, how we could get to this better understanding of uncertainty. And then I'll talk about how we can use the simulations that come out and how machine learning integrated with domain knowledge, the kind of domain knowledge that may not be that adequately captured in the current generation of models, how we can use that for scientific discovery and for downscaling to stakeholder scales. And then I'll just allude to the human dimensions. We have worked on some aspects of that, such as network systems, human-engineered systems. I'll also talk a little bit about the kind of things that needs to be done in these areas. And then for HPC, the idea is that the dream is that we move towards systems that can solve partial differential equations and discrete event simulations and agent-based systems and probabilistic graphs networks, potentially all in the same way with feedback and informing each other. But I'll not talk about all that right now. I'll just allude to a few case studies. I'll just quickly go over them. They're all there. I have citations, and these are easy to find out. Some of them are fairly old by now. So we did some work on heat waves, which showed that the heat waves, the trend of heat waves may be worse than what we think or what we thought then, but the geographic variability may also be higher. Eventually, we also looked at cold snaps, and we found that despite global warming, overall global warming, that's not being disputed here, but at the tails, cold spells may persist. And persistence here, in this case, we had a specific definition. The frequency of cold spells will decrease over time, but the ones that do occur may be as long-lasting and as intense, sometimes even more so, because of the different kind of physics going on. So heat waves and cold snaps. This was one case where we looked at, and again, you could think of these as looking at different model simulations and ensembles, both initial condition ensembles, multimodal ensembles, different greenhouse gas emissions scenarios. These days, we often talk about this ensemble multiplier effect. It's a huge amount of data set. So all these insights come from there. So here, for example, we are looking at coastal upwelling, which is very important for marine ecosystems and caused by differential land-sea heating. And we found that coastal upwelling will intensify in the future, but also grow spatially more homogeneous. So very important finding from marine ecology side. This is more terrestrial ecology. This was very recent, just this month actually. So this talks about temperature fluctuations. People have looked at mean changes in temperature and what that might mean for ectotherms, such as insects. Ectotherms are cold-blooded animals. They are less able to tolerate temperature changes and fluctuations. So what that could mean for them. What we found here is we looked at the triad of changes in mean, changes in variability, and changes in autocorrelation. Changes in fluctuation stood out. So here we looked at these outputs from large-scale Earth system models, but we also looked at field scale, laboratory scale tests, or thermal performance curves of insects based on field and laboratory scale tests. Tried to blend the two, and what we found is that despite diverse kind of impacts of temperature, mean, and fluctuations, there is always an almost universal increasing risk of extinction of these species. The kind of things where we can balance or blend different information from very different sources at very different scales and still obtain some interesting insights in ecology. Now, thinking about these multimodal ensemble then, and the fact that what I'm showing is we can extract insights from them, meaningful insights, important insights, potentially actionable insights. But where are we still? A lot of this, I mean, it's not that we haven't made progress. We have been making significant progress. But there are some issues still there. So I'll just quote two articles, the headlines of two articles from Bloomberg, and the same author of that, I mean, same journalist. In 2020, which is when the latest generation of climate models, these are called CMIP-6, latest generation of climate models started to come out. There was this headline that climate models are running red hot and scientists don't know why. And then 2022, and the generation of models remain the same. So we get from one generation of models to another generation of Earth system models, and their simulation follows roughly the IPCC cycle, the Intergovernmental Panel on Climate Change cycle. We get those in about 7 years, 6, 7, 8. That's roughly the time frame. Nothing changed in those 2 years. The same, I mean, we had some more ensemble runs, but it's the same generation of models. And they're saying, why are some climate models running red hot? Scientists have an answer. So to my understanding, climate science, unlike, let's say, machine learning, doesn't progress in terms of our understanding that fast. So what happened? Well, they're saying that, well, you know, we have to look at climate models, rank them based on the skill in terms of how they work with observations, instead of just looking at this. Now, there's a lot of details that needs to go in there. We have known this for a while, that we should look at skills and consensus. Skill is how these models perform with respect to observations in the past, when we have both model hindcasts and observations. And consensus is how these models agree with each other. So we need to look at both, that we knew. Something is going on which is an indication that we need to do a bit better, at least in terms of capturing the uncertainty. It's impossible to say that we will remove all variability and all uncertainty. There is something called irreducible uncertainty in Earth system sciences. There are also knowledge gaps which we can continue to improve. But in terms of managing that and getting towards climate resilience, we could probably do a bit more. Here is one of our work where we tried to develop a Bayesian scheme based on the work of Richard Smith and Claudia Tebaldi and many others. Here what we are trying to do is look at skills, consensus, like I explained earlier, but also look at physics that may not be that well captured in climate models, such as temperature dependence of precipitation extremes, and see if we can use all three to develop Bayesian schemes, for example, at watershed scales. And here we are trying to get a little bit firmer grasp on this knowledge gap versus internal variability. If we look at multimodal spread, in each of these models developed by 40 to 50 groups around the world, the basic physics has not changed. First of all, Newtonian physics is not changing, and then the parameterizations that we know doesn't change too much, but there are still certain things, the way the parameterizations happen, the way they are structurally built, those may be different. The models have some spread. So that spread represents aspects of our knowledge, gaps in our knowledge. And then there are intrinsic variability in the system, which are also indicated by by internal initial condition runs, multiple initial condition ensembles, which is one aspect, I would say, of the internal variability. Now, if you look at the picture on the, or the set of pictures on the right, and on the right, if you look at the top left one, that's temperature. It's clear that there is a trend in temperature. And if you look at the blue, that's the model spread, and if you look at the red, that's the internal variability. It's clear we still have lots to do in terms of improving or reducing our knowledge gaps, but internal variability is there. But as you go further and further, the contribution of that reduces. But just on the right of that, that's precipitation. And at the top, these two are at global scales. Precipitation is a little bit more unwieldy. It doesn't still reduce, even going into the 100-year period. And then, if you look at some other data sets, as we go to more and more stakeholder scales, from the globe to continents to country scale to cities, we see that this internal variability dominates more than at aggregate scales. What does this mean? We give up? No. It just means we need to have better ways of managing that variability, that internal variability, and the uncertainties that are caused in projections by both knowledge gaps and internal variability. So here is an example. If you look at this was based on an earlier generation of models, CMIP3. Model 1, Model 2, and Model 3 are three of the US models that were used then, NCAR, NASA, and NOAA. I have a citation here. I don't remember which is which right off the top of my head, but those are three models at the top left, the ones that are unshaded. And then the rows are two different initial conditions. These are very small changes in initial conditions, like 10 to the power minus 14 kind of changes, not detectable by any sensors. And here we are looking at something that is a bit difficult to do compared to temperature. We are looking at precipitation minus evaporation. We are looking at 10-year averages of those at 30, and so 30-year differences in the decadal or 10-year averages of precipitation minus evaporation. So overall, in a sense, it gives some assessment of mass balance, what's happening to water. And look how distributed they are. Look how diverse they are. And if you look at the average of all averages, that's at the bottom right, that seems to suggest not much is changing. As a civil engineer, if somebody were to ask me to build a bridge, saying here is mean traffic, please build a bridge based on that, I'd be terrified, because that bridge would fall down twice every day during peak hours, and again when there is more, anytime there is more than mean traffic. Designing based on this average of averages is like that. It is like saying that if we have 40 people that may die because of floods in 1 year in one part of the US, and 40 people may die in another year in another part of the US because of droughts, so floods 40, droughts 40, 40 minus 40 equals 0. If you're willing to live up with that, fine. None of us are, so we have to understand, characterize, and then use in our design and operations this range of variability. Here is one example where you're looking at power production at risk, water stress because of both rising water temperature and net water availability. And what we're seeing here is that the multimodal ensemble gives very diverse, plausible futures. But there are significantly enough number of them which point to scarcer and warmer futures in different parts of the US, especially where energy production happens, and most energy production requires a lot of water. So that's the kind of insights we can get, that we need something, we need to do something. And then some of these things, of course, we can improve with different kinds of things, that different tools and approaches that are coming up with machine learning, like I was already saying earlier. So this is a perspective article in journal Nature, which talked about how different areas within machine learning has been applied to and has been improving different aspects of our predictive understanding of climate. One of the 4 areas was our work, which talked about the use of super resolution computer vision in the context of what is called statistical downscaling, bringing Earth system model simulations at the scales that they are to the scales where stakeholders can use them. But while keeping in mind this issue that will these functions that you use for these functional mappings that you use for statistical downscaling, will they generalize as the climate changes? So I'll not talk too much about them, but we published these in computer science machine learning venues such as KDD. So this integrated some aspect of the physics with computer vision. This was 2017. 2018, the next paper was a realization that the kind of, when we try to look at uncertainty, at that point in time, the uncertainty was still making Gaussian assumptions about data and distributions, which of course will not work for our problems or many science and engineering problems. So we looked at Bayesian deep learning, but quantifying uncertainty in the context of skewed data set. The other thing we have to then realize is how to take all of this, and I showed some examples, but how to take all of this and translate this to a risk framework. So we talk about natural variability and anthropogenic climate change, and together they cause hazards, weather hazards, not any one of them. And then, despite hazards, even if hazards are intensifying, which they are, no hazard by itself will lead to a catastrophic disaster unless there is infrastructural and societal vulnerability. So Katrina is embedded into our collective psyche because that levee broke, but also if there is societal exposure, unless there is societal exposure. So people who were traditionally underserved, had the least resources, were living sometimes in areas below sea level. There's a combination of this. And what needs to happen there is both preparedness, consequence management during the hazard, recovery, but also slightly longer-term adaptation and even potentially even longer-term impacts on mitigation, reducing the hazard itself. And in each of these areas, there are different ways in which integration of physics and machine learning can come in, all the way from the left to understanding climate extremes, better understanding of climate extremes, to understanding how they can be converted into design curves for example, hydraulic infrastructures or other kinds of infrastructures. And then, in the context of specific hazards, looking at the use of AI and machine learning and integrated with physics for short-term predictions. So if we are saying that we are already living under and expecting to live under more and more intensifying precipitation extremes, shouldn't we get better at predicting those? And the other thing is then translating all of this to specific systems, whether it's the infrastructure systems, human systems, and one system we have looked at is regional and urban transportation networks, all the way from US airport network, Indian rail network, London rail multiplex, Boston rail network, et cetera. So we have been looking at these in the context of both floods, but also floods and opportunistic attacks, et cetera, and overall network-based resilience. So talking about natural systems, spatiotemporal machine learning, and then talking about interconnected systems, network-based systems, looking at probabilistic graphs, etc. It's all good, and it all needs to be done, but then there's the human component. This is a paper that was published in Nature, and the red here are all those rivers which are dominated by human components, human decisions, dams, reservoirs, different ways in which humans impact these things. And you'll see that other than in certain places in the world, like the Amazon, the Congo, there are not that many that do not have a significant human influence. So if you think about this, humans needs to come in. So if you think about hydrology, for example, and land surface process models, which are a part of the larger Earth system models these days. Global climate models are now called Earth system models because they include so many components. Not only are the parameterizations sometimes over-parameterized, sometimes misparameterized, because of the heterogeneity of Earth systems, it's difficult to take lab tests or even tests on small watersheds to these large watersheds. But, so there is a scope for enhancements with different kinds of machine learning, but also the human in the loop. Humans impact through hydraulic infrastructures and decisions, so how to bring that. So that's one challenge, and this challenge operates at multiple scales. So if you think of that IPCC risk framework, at the global scale from anthropogenic warming, natural variability, that's where this, the community Earth system models, these large Earth system models operate. At the scale of disaster management, floods, droughts, that's where, just as one example, there is something called National Water Model. There are many other models which operate at those scales. And then in the context of human decisions, whether it's adaptation, mitigation, there are other models. So all of these then need to work together, and human component is important in each one of them. And they then impact things like transportation, things like power grid, communications, water systems. So that's the issue there, the challenge that we are dealing with. Now to end quickly, and in the interest of going to the meaning of life, universe, and everything, so I'll go to 42 slides. This is my last slide. This was actually done as just one slide. I know it's incredibly busy, but just for National Science Foundation, they funded a large project called Expeditions in Computing, where I was a co-PI. The PI was Vipin Kumar from Minnesota. We're just saying what has come out. This project is now over. But what has come out of this, so kind of things we did at our lab, this is just our part of it, which is, we have been publishing in climate science venues, infrastructure venues, computer science conferences, interdisciplinary venues, et cetera. Some of the work we have done has informed both, global scale assessments, like all 3 assessments of the last IPCC report, but also hopefully some action, Climate Ready Boston, Town of Brookline, what used to be called the Sustained National Assessment. And on the right, as I was saying earlier, that what we have realized is financial incentives, social equity, and these methods and tools for climate needs to happen hand in hand. We tried to demonstrate that to some extent with Climate Startup. This was co-founded by me and one of my former PhD students and another student at Northeastern. This former PhD student, Evan Quadra, said, Auroop, you guys are not going to do anything. You're only going to get some science things here and there. So I want to do something. So he opened this. What he was doing is, okay, at the scale of cities, this is climate and cities. At the scale of cities, he said, here is how we can look at what climate change means for it, based on all these models and observations, based on exposure vulnerability. But also, what does this mean for traditionally underserved? So there was a strong ESG, environmental, social governance component. And then if it's a startup, if we have to bring the power of entrepreneurial activity into these problems, because as I showed earlier, they're not being solved as fast as we need them to be solved. So if you're going to bring power of entrepreneurial activity, one aspect of that is monetization. In this case, they monetize that through municipality bonds, so through the bond market. So with that, thank you very much.
Okay, thank you. We have one question online that's essentially asking about, you showed the different models and different initial conditions, and it's asking kind of what is what makes the most sense there is should you focus on a more granular level of looking across the ensemble, of focusing on one parameterization across models?
That's a good question. So if we had infinite number of computational resources, I would say all of that makes sense. Because even to test the hypotheses that to improve cloud physics parameterizations, we have to look at higher and higher resolution models. We need to run some high resolution models. And for cloud physics, which is considered probably the most uncertainty contributing area, or at least one of the most, we need to run those kind of things. However, in the interest of enhanced predictive understanding and informing adaptation and mitigation, I think that's where a little bit more maybe strategic investment is needed in terms of which places we try and improve and how much improvements we can get. And and that's where some of these systems where I was talking about use of artificial intelligence in all its forms, machine learning, probabilistic graphs, agent-based modeling could come in. So I think we have to be a bit more strategic there. In terms of the models themselves, one thing that happens is we have these different model runs and so on. These model runs each time take up so much compute power, take up everything. There are not enough resources left for multi-physics runs. There is limited resource left for multi-initial condition runs, the kind of variability I was talking about. We need to be definitely a bit more strategic about that.
Okay. Well, please join me in thanking Dr. Ganguly. And that concludes this session. Thank you all.